Radiation type gizmo.
Look,
All right,
I
there
just
we
want
go.
a laser that fires alpha, beta, and gamma type radiation in a focused, directed way that can probably give people all kinds of diseases. I don't see why there's a problem.
Well,
All right, guys, so,
laser,
oops, I need to scan these pages, I
The
guess.
gamma rays would be.
but the rest of it would be something else. The particle accelerator.
Beam technically works.
All right, guys, so today I'm going to start the acoustic parts,
Cool.
but I don't know how far I'm going to go because, I mean, it's very mathematical. I just rather give you some concepts, but we can do a little bit. So basically, if you remember, I think at the day of the first class, I kind of, I hope so, John, is what I ask you, is that when you have, let's say, a guitar, a violin or a guitar, okay, a string instrument, what makes the noise? Is it the box? Is it the string?
I remember you saying it's kind of like the string makes the box vibrate, which makes sound waves in there that kind of get out.
So basically, if you put the same instrument in space, are you going to hear music?
No, because there's no. Oh, okay. So air is what makes the sound technically.
So basically, is you disturb the molecules of air, and that distortion is what creates the noise or the music, no?
Mm-hmm.
Okay? And the way you put it on the box is, there's two ways to understand with acoustic, which is not that difficult. The best thing is imagine a water. The first thing is that you need a medium for the sound to travel, no? So obviously here when you say there is air in this room, we cannot say it, so it's pretty hard to imagine, no? But however, if we say, okay, if you look at water, what happens if you drop something on the water? It's going to create some type of wave, no? Okay, and if you hit something, that wave is going to rebound, it's going to start deforming, and so on and so on, okay? So basically you can picture in the air something similar. So what creates the noise is the way you disturb the air. But for example, when we speak, do you think, is it a wave traveling? Yes, a wave traveling from here to there. Yes, and why do you hear me almost simultaneously? It's because, what is the speed of sound?
Something like 343 meters per second.
Something about 343 meters per second. So what is that? Basically, let's see, it would be about, I would say 3.5 to 4 football fields. You put one by each other, no? You say something and that's how fast it will go, right? But it's not really like a wave that travels by, it's not like I say something now and and you're gonna see something moving as fast as over there. It's basically all the molecules of air in this room are kind of connected, all right? So when I disturb one, what's gonna happen? You're gonna disturb the second one, third one, and fourth one, no? You don't see here molecules moving or a wave going to you, all right? You disturb the molecules of air, which will then produce a sound, okay, in your ear. So basically, the two things you need to do is that you need a medium, okay, to have acoustics or wave, and that basically it goes very fast. That transmission through the molecules go very fast at a speed of 43 or 350 meters per second. All right. So we could do the whole derivation, but maybe we're gonna try to find something on YouTube, but I don't know if they have something interesting or not. So why don't we put here YouTube? We're gonna put in introduction to acoustics or acoustics?
Something like that should work.
Acoustics introduction. And that way, even myself might be learning something here. Well, no, but people speaking now, see they have some type of animation. Let's see if we reverse the order. Or maybe we can just start with my explanations if I don't find anything. I think the best thing to picture is what happens on the water when you drop a stone, okay? You see, you disturb the water and then it's gonna start to propagate. And if you hit something happens and so on, no? And then the other thing is that in order to have sound, you need to have a medium. Because otherwise the instrument is not going to play in space, no? Okay? Even though you have the same guitar and everything. So it's not that much the instrument that does itself the music, is the way you disturb the air on the surrounding. Okay? So let's just leave it there. We're not going to try to find something here. All right, so let's start maybe just looking at this. So I will scan this after class and put it online. So what's today, June 19? Are we on 19 or no? I think we are.
Yep, June 19.
All right, so June 19. Oops. I lost something here. Oh. Not here. All right, so June 19, I'm just going to say here. Introduction to acoustics. Okay, so really acoustics, it's strange. I mean, the reason why we call this class acoustics and vibration is because there were more politics than the real material we wanted to cover, is because AE had a graduate class called Vibrations. So we call it Vibrations. The administration gives you a hard time because they say that why then don't you have your students taking that class? Okay? So we have to make it a bit different. So vibration and acoustics. And it kind of look the same, but in real life, acoustics is not that much a structural problem. It's a lot more a fluid problem, for the reason I just gave you, no? What do you really do in acoustics? You disturb the medium of the flow in the surrounding, okay? So it's a lot more related to fluids than it is related to structures or anything else, okay? So here I'm just gonna give you, basically I'm not even going to do a derivation, because to do a detailed derivation we need to go into like fluids, I remember the total derivative, the continuum, the continuous equation for a fluid flow, and so on and so on. So I'm just going to give you the equation and then we're just going to solve it. At least you learn the procedure about how to solve the wave equation, or general equation, all right? The wave equation is the same as then will be the wave pressure equation, which is the same. Either you have a wave, like the one on the water, or the one as we speak, or the one on the music, or what could be the other source of creating a wave. You can do a pressure, no? You have like, let's say this time you have like a drum. What is the drum doing? You hit the side of the drum, so you move the wave by creating pressure on that membrane, no? Okay? And then you move it that way. On airplanes or cars, what do you have noise?
Because the piston moving back and forth shakes the air around.
That could be that, yeah. I mean, that's one way. But what I'm thinking about, for example, you see maybe some people that they like to race the car, okay? What happens as soon as you take them on the highway? They make a lot of noise, no? They flap, because what happens? If you look at the spaces of the tires, because you go fast, you start creating a change in pressure between the empty space, no, and the speed of the car. So that change in pressure, what is that change in pressure doing? It's creating a wave as well. All right? Just like if you take a syringe and you block this one, you pull, as soon as you pull it out, you hear a noise, no? Where is that noise coming from? Because you created a wave by the change of pressure, okay? So in aircraft and cars and so on, most of the time when they drive fast, that's where the source of the acoustic noise comes from, okay? It can also be something vibrating in the structure, but in most cases what is known as acoustic is something which comes from either wave or change in pressure, okay? All right, so let's go there. So let's just say here, for acoustics, you need a medium, okay? In this curve would be air. All right, and just say here if you want. Okay, so you want the noise created by a musical string instrument is produced by disturbing the medium, okay, the air. That disturbance creates a wave. Okay, another example, if you want. I always like to give the one of the string instrument because it's easy to see like the string, okay, of a guitar moving and moving the medium. Okay, but if you think about pressure, what about a trumpet? How do you produce sound with a trumpet? As you try to play a trumpet, you need to blow pretty hard in it, no? Or a saxophone. And then you blow, you create pressure inside, and then with the instrument, what do?
Basically change the length of the tube.
You change basically, yeah, it's a good way. Yeah, you change the wavelength of the pressure, but basically you change the pressure, no? By releasing pressure, opening one valve, closing another valve. And that creates a wave by this time looking at the pressure, okay, instead of moving one string. But the concept is the same thing. You need to change the medium, which in this case is in the air. And the way you disturb the medium is by creating a wave, and the wave is the one that transfers the noise. And the noise travels at what speed? At the speed of sound, okay, which is about 350 meters per second. All right, so the equation describing that phenomena is given by, so will be, it can be any variables. You gotta use u, but so partial of u partial t squared. And obviously this is a simplified version of it. Partial u partial x squared. So over here it's basically the same thing that we have been doing, and the procedure will be the same. In this case over here, u is in function of how many variables itself?
2, at least.
2 at least, which will be?
X and T.
X and T. Okay. So obviously you can imagine that we can make this equation a lot more complicated. So in this case, for example, this will be the equation like this will be kind of your wave. So it's changing what? It's in function of time. So you see that u changes in function of time, no? But it's one-dimensional. So this is the one-dimensional version of the wave equation. The real derivation of that equation can be quite complicated. I mean, the derivation is not that straightforward. That's why I'm not doing it. And in addition to that, if you go to the full equation, it has a lot more terms. So, in other words, do you think the wave equation is influenced, for example, by the temperature? Do you think the music will be the sound the same if you have a certain temperature or another?
I mean, change probably is not that good, not that bad, but I'm sure there will be a change.
That's what happens, you know, it's like, it will be a change. You can also think about will be a change with respect to altitude or pressure, you know, density, all those things. It will also be a change. So we start taking everything into consideration, we end up with a very complicated equation, but this is the more simple form of the wave equation, okay? So this is known as, if you want, the one-dimensional, 1D wave equation. Okay, so in order to solve that differential equation, so we know we have one variable, which is u, but which is in function of x and t. So, and we have it on the right-hand side, second degree of freedom, okay, 2, second degree, second degree. So how many initial boundary conditions do you think we need in order to solve that differential equation?
I want to say 2 or 4, but I'm not sure which one.
Basically, we need 2 in order to solve u for t, no?
Mm-hmm.
And we need another 2 to solve u for x.
Okay.
Okay? So what happened is that, this is just, so you need 4 conditions are needed to fully solve the wave equation. So I don't know why people want to make fancy, but basically you have some of them are called boundary conditions. And some will be called initial conditions. So I don't know why. To me, they're just conditions. Okay, they're gonna have. If you go to mathematics, they're gonna have different names because they're different type of boundary conditions. But boundary conditions generally would be the ones related to what? To the geometry, and initial condition would be based on time.
Mhm.
Okay. So boundary condition, what could you say over here? U x. I don't know. Equal. So some initial displacement, all right?
Mm-hmm.
And then, I don't know, you could do the same thing for the velocity, no? Okay, and here you can say t initial equals 0, let's say, and t final equals to whatever,
Mm-hmm.
t over here, okay? So in most cases, what would they tell you? The displacement at x at t equals 0, okay, will be, let's say, a certain value, okay? But we'll do that later. All right, so basically we have this equation. We need boundary conditions, initial conditions, 4 of them in order to solve the equation. All right. So last number. What was the last page we had? 104. Okay, so in the previous chapter, what did we do in order to solve the differential equation?
We assumed a certain form of solution and then substituted it into the equation.
Perfect. So the first thing to do is to assume form of the solution, no? Okay, so in this case, we say what? That u depends on 2 variables, x and t. So our assumed solution, what could be our assumed solution? What would be the maybe the easiest form.
Sine or cosine?
Okay, but that will be very specific in general. Basically what I need to do is that solution needs to be in function of x and t, no? So we could say that the solution will have one function that we call phi, that will be in function of x,
Alright.
okay, times a function, let me see how I call it on the notes, h in function of t. Okay? So
Alright.
this is our assumed solution. Now, what is the second thing we need to do? You just mentioned it. We need to go and substitute into a wave equation or differential equation. So let's see, what is our equation? Let's just recall it. Our original equation is second derivative of u with respect to t squared equal to c squared, second derivative of u over x squared. I forgot to explain what is c, but I'll do it as soon as we pass the next step. So in this case, let's see, what would be, this is our assumed solution, what would be the first step? What would be the second derivative of u with respect to t squared?
Would it be phi of x times h double prime of t times dx dt?
Okay, so will be a second derivative of h dt squared, no? All right, so this will be this one, and what will be the one for the x?
Would be d phi dt second derivative and times h of t.
Okay? So, once we substitute, what do we get? This one will become phi of x, second derivative of h dt squared will be equal to c squared, second derivative of phi dx squared, h of t. Alright, so now let's go back to the basics. Okay, I always try to teach you procedures more than a lot of mathematics. Once you did your separation of variables, now we should be ready to solve, no? But before solving, what should we try to do? Now let's look at the equation. This time we have, previously we only had one variable, no? This time we have two variables. So what do we need to do with those variables before solving?
Find a relation between them?
We need to try to separate those variables so that then we can integrate or differentiate, no?
Okay.
Okay, mostly will be integrate. So we need to separate the variables so we have all the same variables on one side and then the other ones on the other side. Okay? So we do that. That's why this method is called what? Separation of variables, no? But, I mean, it's just to use your common sense. So let's say I'm going to move, so c squared is a constant, so you're going to have c squared. I'm going to move all these ones at the same place over, let's see here, 1 over phi of x. Yeah, so I'll move this one to the right, second derivative so I'll move this one over here, and that will be equal to what?
It would be
To 1
1 over h of t times d squared h d t squared.
dt squared. Okay, so here I forgot to give you this, but I'm going to mention it now over here, sorry for that, is that where C, or C squared would be easier, C squared is T over rho A, where T is the tension, think rho is the density, and A will be the cross-sectional or the area, okay?
Mhm.
All right, so I'm pretty sure you know the answer. I just give you here the expression, but what do you think is C?
The speed of sound,
Is the speed of sound. So if we are correct, what should be the units for C?
meters per second, or length of time.
Okay, so it should be meters per second. So hopefully we'll get meters per second, no?
Mhm.
So let's see what we have over here. So we're gonna have for the units, we have C squared equals to T divided by rho A. What will be units for the tension?
Newton,
Newtons. What about density?
kilogram per cubic meter,
Kilogram per cubic meter. And area?
square meter.
Square meter. So what would be 1 Newton?
1 kilogram meter per second squared.
Kilogram meter second square. And now we simplify this, we have kilogram divided by meter, no?
Mhm.
So we simplify this, we end up with what? The kilograms cancels out, no?
Yep, and you get meter squared per second
And
squared.
we get meter square per second square, or C will have units of meters per second, no?
Mhm.
Okay? So C is also known as, so C is known as the speed of sound, which is approximately 350, I know it's a little bit less, I don't know why it's 240 something, but let's say 350 meters per second. Okay? So to give you an idea, if you want 1 meter is about 3 feet. So it will be about, how long is a football field?
What was it?
Okay.
Something like 3,000 feet?
3,000 feet?
300.
Oh, 300, all right.
300, so 300, yeah, it's probably about 100 meters, I would say, 300. And it would be what, about 1,000 feet, so it's more than 3, no? It's more than 3 and a quarter, 3 and almost a half, no? Somewhere between. So it's basically what I say, it's about 3.5 fields. If you just say in 1 second, that's how fast the speed of sound is going. But it's not really that it's something, what I don't want you to think about it is that it's something moving really fast, okay? It's more that all this room is made out of molecules. Imagine you have, whatever, tennis balls, okay? And what happens if I deform one tennis ball over here? It's going to start deforming all of them, no? So that's more the way this works. It's not that I'm going to throw here something to you that is going to go at 350 meters per second, okay? No, what I'm doing is that I'm disturbing here a little molecule, but the way that disturbance goes to molecule up to you, or to tennis ball, ends up being about 350 meters per second, okay? So I want you to think about that, because that's the big difference, okay? It's a lot of change about, I'm changing the energy or the kinetic energy of this one, and this is going to create an effect that's going to go all the way up to you, okay? All right, so now we need to go back then 1 second to the solution. Okay, so this is the equation. So now if you want, so you can go to textbook, you can say here, using separation of variables method or technique, which is what we already did, okay? This is what this equation is. But basically what the equation is saying is that the way to find the solution to this is that we're gonna have c squared, I'm gonna start simplifying the notation, 1 over phi, some derivative of phi dx squared is going to be equal to 1 over h, so the derivative of h dt squared, and that this, okay, is going to be equal to a constant, all right? So both of these equations need to be equal to the same constant. And guess what that constant is going to be? Will be, lambda will be an eigenvalue. Remember, we use the same notation for the other ones, no? Lambda is really an eigenvalue. So you want, put here lambda eigenvalue. Okay, so for this to be satisfied, what happens? So we can write the above equation is always the same. This would be like if we go to the characteristic equation, no?
Mm-hmm.
Okay, the above equation is satisfied if what? If this time we have two equations, so if c squared 1 over phi second derivative of phi over dx squared equal to minus lambda, here you could put plus lambda, okay? Minus lambda, you will see why we use minus. And what will be the other condition? 1 over h, this second derivative of h dt squared equals to minus lambda. Okay? Because if both of them are equal to the same value, then this needs to be satisfied and this needs to be satisfied, no? And if that is satisfied, that means that both equations should be equal to each other. Alright? That makes sense? So now what we need to do is solve those two problems. So we need to solve this problem over here. So let's say this would be equation 1. It would be equation 2. So if you think about it, the solution of this one will give us the solution of what? Of phi, which is the part of the deformation, no?
Mm-hmm.
And the solution of this one, of h, will give us the solution for the time, which will be given by the function h of t. Okay? That's basically what we are doing. So let us solve first, let's say, the equation for phi. All right? All right, so I have here on the class notes that as an example, let us solve the wave equation for, so here we're gonna have one string So the distance between is L, and here I'm going to take the conditions what? U at x equals 0 at t equal to 0, and here I'm going to say U of L at t equal to 0. So, all right, and let me do one more thing. Okay, so this will give you the boundary conditions, no? And now we're going to say that U of x at t equals 0 equal U sub naught, and that the velocity, so partial U partial x, let's say at x and at t equals 0 will be equal to U dot 0 or V0. All right, so first, solving the first equation first. So solving I first. So what is that equation? C squared, 1 over phi, second derivative of phi, dx squared, equal to minus lambda. Now, what should be the boundary condition for this one? So, for this one, we have the boundary conditions, U what would be the two conditions to solve this one? Would be U of 0t equals to 0, no?
Mhm.
So this, if we write this in function of phi, what would that mean? Let me write the first one. Phi of 0 would be equal to what? 0, no? Okay? Second condition is U of L t equals to 0. So what would be this one?
Phi of L equals 0.
Equals 0. Okay? So we need to transform our boundary condition into that variable. And now we can just go and solve. So now, this equation is the same type of equations that we had on the previous chapter. So, again, same procedure. What is the first thing we need to do?
Assume a certain solution.
Assume a certain solution, but this time we only have one variable, no? Assume solution. What do we assume before as a solution?
Harmonic, some kind of exponential function.
So here's going to be the same thing.
Alright.
So P naught E, and I already used lambda here, so I need to use something different. And I'm going to use, I can put the negative or the positive. It really depends. I have the solution here with the positive, but if you want, you can change, okay?
Alright.
But I'll just do it with SX. If you want, you can put negative, okay? It should not matter at all.
Alright.
You want me to change it, or
Oh, that's fine.
let's leave it like that, otherwise I won't be able to change. So now that we have this assumed solution, what do we do with it?
Plug it back into the equation.
All right, so you see, guys, once you learn the procedures, all the time the same thing, no? So substitute into I. So I need to go to the next page. And I'm going to run out of paper. Okay, so remember, we need to substitute.
Phi and the second derivative of phi?
Yeah, let's do one by one, that way we don't. X, so we take the first derivative. What do we get?
S phi naught e to the sx? Yep.
If we take the second derivative,
I don't think the x should be there.
the x, no x here. The second thing would be,
Phi naught s squared e to the sx.
so now remember we need to substitute, yeah, let me just write it down. We need to substitute into this equation here, c squared 1 over phi, second derivative of phi squared equal to minus 9. So we substitute into that equation, what do we get?
C squared s squared equals negative lambda.
C squared S squared. So we got C squared, wait, I do the first one. Yeah, you're right, but you went a little bit faster than I thought, okay?
Okay.
Because it's going to be divided, so, yeah, so C squared S squared P naught E S X divided by P naught E S X equal to minus lambda, which you are right, this cancels out, this cancels out, this cancels out. So we have C squared S squared equal to minus lambda, or C squared S squared plus lambda Why am I doing this? I'm trying to solve now for lambda, no? Yeah, so this is correct, but I was just going to go back. Or here you could say that lambda, or S, no, I'm trying to solve for S. S will be equal to what? So S squared equal to 1
over c squared times negative lambda.
okay, then lambda. Yeah. Now I'm going to put, and again, or S should be equal to what?
I guess you could say square root of lambda I, or plus, yeah, plus or minus.
Yeah, we got plus or minus because here you have the negative, no?
Yeah.
1 over C square root of lambda. Okay, so what's going to happen here now?
Would you substitute it back into your phi equation and use the boundary conditions to solve for phi naught?
Correct, but remember, lambda is a constant, so the lambda could be what? Could be positive, 0, or negative, no?
Mhm.
So basically the solution will then depend on the value of lambda. But you're right, basically now you will go back to this one and substitute back into this equation. All right? But we have different type of solutions depending on the value of lambda. Okay? So what do? You want me to go and substitute and then find a different solution? So we just do the different values for lambda now. I'll just do now for this. So they say for lambda, negative. So that will be good. So that will mean what?
S equals plus or minus square root of lambda over c.
Yeah. So we'll have this, no? So we do the easy solution. So now we go back and substitute into the solution. So the solution P of x equal to phi naught E as x, s times x becomes what? We'll have phi of x will be equal to term p1 exponential of, let's say, minus 1 over c square root of lambda x plus p2 exponential of 1 over c square root of lambda x. Okay, so now, how do we find phi1 and phi2?
You use your conditions.
Okay, so to determine, this is the same as before, no? To determine the constants of integration, we use the boundary conditions. So, to determine P1 and P2, use the boundary conditions. So what are the boundary conditions? Phi of 0 equals 0, no? Remember, right?
Yep.
So this one will give you what?
It would give you phi1 plus phi2 equals 0.
Phi1 plus Phi2 equals 0. What was the second condition?
I believe it was phi of L equals 0.
Yeah, because it was. So this one will give you what?
Be phi1 e to the minus 1 over c squared of
So
lambda
would
L.
be, yeah, would be, okay, so let's do a complicated way. Phi1 exponential to minus 1 over c square root of lambda L plus Phi2 exponential of 1 over c square root of lambda L. So we could rewrite this yeah, so that's it. So we need to solve this and equal to 0. So how do we solve this? We could just replace phi1 or phi2 from the first equation to the other one, no? So let's just say right, solving the two equations for phi1 and phi2. So let's do it because I don't have the solution. So even though I think this is going to be pretty easy, when is this going to be satisfied? All right. So let's say from the first one, let's say that phi1 equal to what? Negative phi2. And now I'm going to substitute that equation into this one. So I get negative phi2 exponential of minus 1 over c square root of lambda L plus phi2 exponential of 1 over c square root of lambda L equal to 0. Okay, so this is, let me do one more step, but this is pretty obvious. So we get here phi2 factor of not complicated, of E1 over C square root of lambda L minus E of minus 1 over C square root of lambda L equal to 0. So what is the only case? Can the exponential be 0 over here? All these are constants. C is constant, lambda is a constant, L is a constant. And we know that lambda here is what? Negative, no?
Mm-hmm.
But can this be 0? The exponential function can be 0?
No,
No.
not truly.
This one cannot be 0, no?
Mm-hmm.
It is not 0. So what is the only option here to have this equal to 0? Is that is phi2 is equal to
0.
0. So here, above equation, satisfy if phi2 equals 0. Next, what do we know? Phi1 equals to
0 as well.
yeah, well, because we use equals to minus phi2, which needs to be equal to 0. So basically, what do we get over here?
0.
Yeah, so for lambda, conclusion, for lambda negative, we get that phi of x equal 0, no? Which will basically will be our trivial solution, which has no physical meaning. So let's say trivial solution, because it's 0, no physical meaning. All right, next, we need to use, obviously I'm doing the cases, the short ones at the beginning, because the one of physical interest, what do you think? Is going to be the long one, no?
Mm-hmm.
So the second case would be what? 4 lambda equals 0. So in that case, if we go back to the initial equation here,
Then s equals 0.
what are we going to have?
S equals 0.
So we have here that yes. Okay, so we have that, let's go here, S equal plus minus 1 over C square root of lambda. So S equals 0. But if S equals 0, what does that mean for the assumed solution?
Phi of x is a constant.
Phi of x, not phi of x, no? All right, let me go back for a second then here. I think it will be easier if we do it this way. Don't write anything yet. Okay, let me see if it's going to be more clear this way. If I stay at this step over here, this will mean what? That c squared, s squared plus lambda equals 0. Okay, or S squared plus lambda over C squared equals 0. Okay, and now this is different because if lambda equals 0, what does that mean?
That term is 0.
That's equals 0, but this expression becomes what?
S equals 0?
The same as before, but I'm trying to find is that we're trying to solve for S.
Mm-hmm.
Right, let me go back 1 second because I know what I need to get, but I need to be able to show it. All right. Oh, I think I got it. Oh, no, no more paper. I need to go get paper. Maybe we're gonna redo this part, okay? This is not bad, okay, but just gonna write on different form. I'll be right back. You do that to my office, get paper.
So apparently I can draw a mouse in the best, but I cannot draw Heinz driven shorts.
What was the lightning when you just got that?
Not sure whether I made this chin too big or too small. It's confusing me.
It doesn't rather large one.
It just makes hair too big. Well, definitely makes hair too big, so it might be worth me to check. You end up looking like a bird.
All right, so let's go back here and let's start a bit from more the beginning here. So okay, this 121. All right, so for lambda equals 0. Okay, here there's nothing wrong that we're doing, but how do we obtain the S squared? Because we have to take the second derivative, no?
Mm-hmm.
So read that the S squared equal to 0 means that the second derivative needs to be equal to 0.
Mm-hmm.
Does that make sense or no?
Yes, sir.
Okay, but I'm going to write out a different form, might be a bit more clear. So our original equation is, where is our original equation? So our original equation was, I need to find it, 120, 119, is this one here. The original equation is C squared 1 over phi, second derivative of phi dx squared equal to minus phi. It's the same thing as saying that S squared, no? But here I think it's going to be a little more clear. We're going to have this. This is going to be equal to what? What you want? This should be equal. If we leave this one, would be second derivative of phi dx squared plus 1 over c squared
times phi lambda.
Yeah, lambda phi, no? Yep. It's the same thing as before. So now, what happens if lambda equals 0? This time equal to 0, no? And now, this is what I was trying to show before, but I think so then this needs to be equal to 0. Okay? It was the same thing as saying that here, you see when we had s squared equal to 0, and we knew what? That phi double x was equal to phi naught s squared es x, but I think it's more difficult to see it from here, no? Okay? That's why I decided to go this way. So now, what is the solution of this system? In order to solve this, what do you need to do? You need to integrate twice, no?
Yep.
So if you integrate once, what do you get?
Some constant.
So you will get, solution of this will be d phi dx will be equal to some constant a, no? Okay? And then you will find then that phi of x will be equal to what?
Ax. Plus
Ax plus another constant b. Okay? How do we find a and b?
using boundary conditions or initial
Alright,
conditions or
so
whatever.
we do boundary conditions again, so we know, let's go a bit faster. Looks what color did I use before? They use blue. Phi of 0 equals 0 will mean that a, no, b,
Yeah, b equals 0.
b equals 0, no? And then phi of l equals 0 will mean that al equals 0, which is only valid if what?
A equals 0.
A equals 0. So again, for lambda equals 0, what is the solution? Phi of x equal
0.
0, no? So we said as before, trivial solution. No physical meaning. We can organize a little bit because now we're going to get to the one that has physical meaning, no? Otherwise it will not be fun. I think I forgot to put the page on the back of this one. There's going to be room. That will be my next call. All right, so let me organize this one because we have a lot of pages today. 121, 119, 118, 117, 116, 115. Okay. So obviously now, what do we need to do? For lambda higher than 0, no?
Yep.
Okay. So in this case, what are we going to get? Now I lost the equation. What do we have? S squared equal to plus minus 1 over c lambda? 1 over c squared over lambda?
Yes, that would be S. U square root of negative lambda.
Of negative lambda, no? Okay. Okay? Or, what does that mean? S squared. So what is negative of minus 1? Is I, no?
Yep.
So we could say this would be S squared equal to plus minus I of 1 over C square root of lambda. Okay? Was that S or S squared?
It should be S.
Should be S, no? Well, you know, trying to do it by memory, but it doesn't work, so it's S. Okay, so the solution becomes what? So we have, we do it in blue, we have P of X will be equal to what? P1 exponential of minus I over C square root of lambda X plus P2 exponential of I over C square root of lambda X. And this is basically, this whole solution is identical to what we have in vibrations, no? So remember we had that long solution, this was for the damping case, right? So, what do we do? Do I just give you the general solution or do I do everything? All right, let's just finish today this one, the P of X, and we'll do tomorrow the other one. The other one is a lot faster. Okay, so there we go. Okay, I'm just going to try to do it this way. I'm sure I'm going to put myself into trouble. Now, let's just do it the long way. So using Euler identities, which we already used in vibrations. What are the Euler identities?
E to the I theta equals cosine theta plus I sine theta.
Yeah, and E minus I theta, cosine theta minus I sine theta, no? Sorry for that one here, it's not clear. So if I substitute into this expression, what am I going to get? P of X equals P1 of
Cosine of square root of lambda over Cx.
So cosine of, yeah. Wait, is minus, is cosine of 1 over C square root of lambda, no?
Times x.
Times X. Minus
Yep. Minus the sine
I
of the same.
sine of the same. Plus P2, basically the same but with a plus sign, no?
Yep.
Cos 1 over C square root of lambda. X plus I sine 1 over C square root of lambda X. So we combine terms. What do we get?
Yeah, V1 plus V2 times cosine.
V1 plus V2 times cosine of lambda x over c. It's going to take less space if I write it this form.
Plus V1, or V2 minus V1.
Times I, no?
Yep.
Sine lambda x over c. Okay? Or dx equal a cosine square root of lambda x over c plus b sine square root of lambda x over c, where a equal v1 plus v2 and b would be equal to v2 minus v1. Okay, now how do we find A and B, or V1 and V2? It's the same thing,
Use initial conditions?
initial condition. Oh, there we go. So applying really in this case for X we call them boundary conditions instead of initial conditions. If you go to partial differential equation, they call them Dirichlet boundary conditions, but forget about those things, okay? All right, so what were the boundary conditions?
Phi of 0 equals 0.
So this will give us what?
We'll give you that A equals 0.
Because K of 0 equals 0 will give you, yeah, A, this will be 0, no? This will be 1, so will give you A equal to 0. That's not a bad thing, huh? Now, what is the other one? Phi of L must be equal to 0. So this will give us what? B sine square root of lambda
L over C.
L over C must be equal to 0. So obviously here one solution will be B equal to 0, but that's not what we're looking for, no? What could be the other case? When is sine equal to 0?
When its argument is an integer multiple of pi.
Correct. So basically, here is 0, no? Here is 0, no? Yep. So this is equal to 0 when square root of lambda L over C equals to n pi, no? Yep. Okay, so now we're trying to solve for what?
Lambda?
We try to solve for lambda. Yep. So we solve for lambda from this equation. What do we get? Square root of lambda equal n pi
C over L.
C over L. Or if we solve for lambda, lambda would equal to what? N pi C over L square, no? Or really, we could leave this one here, doesn't matter. Or this one, really, I think this one was more appropriate. Because now what can we do? We can go and substitute back over here, no? Which means that, okay, so phi of x at the end, let me just rewrite this, would be equal to what?
B sine of n pi.
B sine of n pi x over L, no? Maybe I went too fast here. Let me just go back. This is correct, but let me go back. So basically from here we get that what was our phi of x initially was a cosine square root of lambda x over c plus b sine square root of lambda x over c. So we know that on the assumed solution, what is a? 0. So it gives us at the end that phi of x is equal to b sine square root of lambda x over c. But what is square root of lambda?
N pi C over L.
And by c over L. So at the end we get that phi of x equal to b sine n by x over L. Okay, so here now, any questions so far? I mean, all mathematics so far, no? So now, what's important is that, what is the physical meaning of that solution?
That function's a wave that starts at 0.
So basically we have, so remember, our problem, initial problem was to have a string which is, if you want, simply supported or held at the two ends, no? All right? So we kind of discussed this before. So the solution we have over here is phi of x equal b sine n by x over L. Okay? So independently of the value of b, what would be the solution if n equal 1? What do you have for phi of x? B sine pi x over L, no? So one way this could be formed would be what? And you think about a string,
It would be, yeah, just a dome like that.
this would be the first one, no? Yeah? Now, what could be another shape of deformation? This would be equal to what?
B sine of 2 pi x over L.
So what would that be?
Be a complete period of the sine function.
Would be complete period of the sine function, no? So you see that this solution here, phi of x, really has multiple of solutions. Remember when we had the discussion of the mode shapes? Okay? This is basically the same. If you take a string, you can move it under these ones, and then you can move to n equal 3, no? Okay, and so on. So really the solution for this one, so the solution, the general solution for P of x is what? Because you don't know what n is, will be the summation of the coefficient of b sub n sine n by x over L. If you want, this would be n equal to 1 to whatever. It's not infinity, but we'll just put infinity. Okay, so let's go back to the beginning. So that phi of x is what? It's only half of our solution, no? Now what do we need to solve for?
HT.
HT of x. So we're going to let that for tomorrow, no? See, today we had enough pages. Yeah, I told you it wasn't going to be that fun, no? Wait, the acoustic part. We can do something more applied if you want. More just talk about what is noise, how do you measure noise, and do something with math. Okay, so we continue tomorrow to solve for h of t. Which is probably going to be another good amount of pages, huh? That's why I wasn't looking forward too much to this section, huh? This is really, I mean, I don't know if you took the class, the math class, which is called partial differential equations. When you take a class in partial differential equations, you solve basically 3 types of equations. One is the wave equation, this one. The other one is the one you do heat transfer, which is called the heat equation. Okay? And then the third one, what it is? What's the other big one? So this one is the second order. The heat equation is constant, but second order as well. And then you solve a third type of equation. I don't remember which one it is, okay? But that's what you do during the whole class. You solve heat equation, wave equation, another one for different boundary conditions. And you go about all this method now, because here we didn't solve still for the coefficients B of n, no? And then you need to solve for all those coefficients for different problems. So this is really partial differential equations, but it is what it is.
Cool.